So now we're looking at percent solutions. Percent means 100 per 100. So we're looking at percent by volume. The volume of solute over the volume of solution times 100. Indicated by percent V over V, volume over volume. Most of us have 70% isopropyl rubbing alcohol, also propanol, called propanol. This basically just means it's 70% isopropyl rubbing alcohol in water, as opposed to 91% isopropyl alcohol. That would be in 100 mils of water. So we would have the solute is the alcohol, solvent is water. So this would be 91% alcohol, of course. This would be 70% alcohol. And then this one is 99% alcohol and the rest water. So that's pretty, that's a high volume right there. Let's just do some calculations here. And we have methanol. What is the percent solution if 25 mils of methanol is diluted to 150 mils of water? So we're just going to use that formula, volume of solute over volume of solvent times 100. So I guess the hardest part really is to decide what's the solute. This would be the solute. And here's the solvent. And so we just have 25 mils over 150 mil times 100. Now, because they're both milliliters, they'll just cancel out. But normally we would change into a liter. But in this case, because they're both milliliter and it's just a percentage, the units will cancel out. We can use milliliter or liter here. And so we get 17%. So that's a 17% solution of methanol. There's something called percent by mass. It's the same concept where we have a mass of a solute over the mass of a solution, and also indicated percent mass over mass. And it is more common to use it like this. And let's try a problem. We have 4.8 grams of sodium chloride dissolved in 82 grams of solvent. 4.8 grams. And we're just throwing it out here, 82 grams of solvent. And we get 5.9%. How many grams of salt are there in 52 grams of a 6.3% solution? So we just have our percent equals mass over mass. We want to change that percent to a number we can work with. 0.063 equals salt, grams of salt in 52 grams. And it's just an easy multiplication there. So that'd be 3.3 grams of salt. We don't know what type of salt it is, so we'll just leave it at that. Now we're going to get into colligative properties. Now colligative properties are very important, and we use colligative properties every day, different types of it. So let's get into it. Colligative properties depend on the number of dissolved particles, not what kind of particles. So this is actually kind of interesting. Doesn't matter what type of particle, it's just the number. How many pieces? So we really need to understand how many pieces things are. Now we have to remember how things dissolve. Remember, like dissolves like. So if we have a polar compound, it will dissolve another polar compound or an ionic compound. Things with charge will dissolve other things with charge. Things with charge will not dissolve things without charge. Things without charge will dissolve things without charge. So nonpolar will dissolve nonpolar, polar dissolve polar. So electrolytes will form ions when dissolved. That means it's more pieces. So remember, electrolytes are ions or polar molecules. The more pieces you have, the more particles, the bigger effect. So let's see, this sodium chloride has two pieces because this dissociates. Sodium chloride 2. They break up into two ions because that's an ionic bond. Calcium chloride 3 pieces. We have the calcium and the chlorine and the chlorine. Aluminum fluoride, 4 pieces. Aluminum, fluoride, fluoride, fluoride. 4 pieces. So this one is going to have the bigger effect. Bigger than this and bigger than the sodium chloride. Now this one, you might think, wow, look at all those particles. But this has 1 piece. As it is molecular, it won't dissociate in water, for example. It is not an electrolyte. Since it's not an electrolyte, it doesn't have any more pieces, just 1 big piece. It won't have an effect like the ionic ones. Will not have an effect like aluminum fluoride or calcium chloride or sodium chloride. A number of pieces have a great effect on the vapor pressure of that substance. And remember, the vapor pressure is what dictates the boiling point. A short review: the vapor pressure is the pressure caused by escaped vapor molecules in a sealed container. So remember, we have all that vapor from the escaped molecules that will create a vapor pressure. And when that vapor pressure equals atmospheric pressure, we have boiling. So this is the vapor pressure created by all those evaporated molecules. But there's attraction or interference between the solute molecules. Will keep the solvent molecules from escaping. So example, the solute would be like sodium chloride. The solvent might be water. So in that solution, some of the solvent is busy keeping the solute dissolved. So like the water is busy keeping the salt, sodium chloride, dissolved. Thereby, fewer escape, fewer leave. Which means, since fewer molecules here, we have less vapor pressure. Here we have pure water down here, and we have a vapor pressure. The molecules will leave. But once we add solutes, such as salt, that lowers the vapor pressure, because instead of leaving, these molecules are busy dissolving the solute. So there are not as many particles here. There's not as many water particles. So that means the lower vapor pressure. Another diagram. Okay, here in System A. In System A, the liquid particles easily shift into the gas phase at the normal boiling pressure. There are no obstacles for the liquid particles as there is in System B. In System B, the solute particles prevent the liquid particles from escaping the system to turn to gas. This requires the liquids to possess more energy to become a gas. So we're going to have much more energy now to get these guys out, to build up that vapor pressure again. It's going to need more energy to get these guys out. Instead of being busy with these solutes, we're going to have to get some more energy there to build up that vapor pressure to get boiling. Now, boiling point elevation, this all has to do with boiling point elevation, or increasing the boiling point. Recall, the vapor pressure determines the boiling point. When vapor pressure equals atmospheric pressure, we get boiling. Solutes will lower the vapor pressure. That means you're going to have a higher boiling point, more temperature to get those guys boiling. Since the vapor pressure is lower, we're going to have to apply more heat, thereby raising the temperature, thereby getting a higher boiling point. So you're going to need more energy now for the vapor pressure to rise to atmospheric pressure. So let's give an example here. Let's say here's Sacred Heart students, and on a normal day, there's vapor pressure here. This says students create the vapor pressure. Some students escape, but once that vapor pressure equals the atmospheric pressure from outside, then you guys all boil and leave. So at the end of the day, you guys have enough energy to finally boil and all leave. It takes all this time from 8 a.m. to 3 p.m. to give you enough energy to leave the school. When the teachers say, okay, you guys can go 3 p.m., that's that final energy that can get everyone to meet the atmospheric pressure. But let's just say there's a distraction. Instead of the normal day at 3 p.m., we have a visitor. Hey, it's Cody from Heartbeat Boys. Now, once Cody comes, hey, look at this. Well, we're going to get some people. My gosh, Cody's here, so everyone's going to sprawl around Cody from the Heartbeat Boys. And what does that mean? All you students are busy with Cody, and there's less of you guys out here. There's less vapor pressure. The vapor pressure is now going down because all the solvent, which would be the students, would be gathering around Dreamy Cody, and the vapor pressure is going to lessen. So we're going to have to get more energy to get you guys out. Instead of 3 p.m. we say, okay, you guys leave. It's now going to be, hey, get out of here. More energy. And then what happens if Noel comes? Well, some other people, wow, hey, Dreamy Noel. They're going to gather around him, and even less vapor pressure, because instead of people leaving, they're going to want to stay and see Noel. And then we get Dreamy Anthony, and hey, Dreamy Anthony is going to come. We're going to get less vapor pressure because, hey, we're not going to leave school. Heartbeat Boy Anthony's here. And then we got Dreamy David. David's coming. And even less vapor pressure. And hey, Ryan. All of the solvent, which is the students, are being distracted or attracted or blocked by the solute, which are the Heartbeat Boys. The vapor pressure is much lower. Look at this, barely any vapor pressure. So that means we're going to need a lot more energy to get you guys out. And we're going to have to say, hey, instead of saying, hey, 3 o'clock, you guys can leave, you guys all leaving, we're going to have to say, get out, get out. We're going to have to really apply some energy. We're going to have to physically push you guys out. And now the more particles, notice as we had more and more of the solute in here, the vapor pressure got less and less. Now what happens if we add Varsity Fan Club? What if they showed up? Well, the vapor pressure is even going to go down, and it's going to be even harder for you guys to leave school. We're going to have to apply so much energy. So this is the principle behind adding stuff or adding solute to solvent. It really raises the boiling point because we're going to need so much more heat, so much more energy to get the vapor pressure back up to where it equals atmospheric pressure. And that's going to require a lot more heat. That's why we add salt to food or water when we boil. So salt water will boil above 100 degrees. And of course we add it for taste too. But if we add salt to water for your deluxe macaroni and cheese, I mean, this stuff is the bomb diggity, as the teens say. You go home, hey, Mom, I want that deluxe shells with Velveeta. This is what it looks like. It has that little pack. That cheese is really tasty. I don't know what's in it. Maybe some old orange peels and some used tires, but I don't know what else. But it really tastes pretty good. You want it fast. You want it to boil at a higher temperature. So you add solute, the salt. That salt, you add more of it. It's going to take maybe longer to boil. You're going to have to add more heat, but it's going to boil at a higher temperature. When it boils at a higher temperature, the noodles will cook faster. It's because it lowers the vapor pressure, and you're going to need more heat to get that vapor pressure up to atmospheric pressure. Actually, I'm going to go have some deluxe macaroni and cheese.